Good afternoon, students. So in the last class we discussed the binary ripple counter, right? Which is also called as an it is asynchronous counter, right? Why it is called asynchronous counter? Because the output of one flip flop is given to the control input of next flip flop, right? So where the control inputs are not simultaneously connected to a common signal called clock, right? So for that reason, the counter which we discussed in the last class is called an asynchronous counter, right? So in today's class we will see a synchronous binary counter. Synchronous binary counter. Why it is called synchronous here? Because the control signals of all the flip-flops are connected to a common signal called clock, right? So here I'll show you how the connection will be. I am going to show you only the connection here. It is not the actual counter circuit. Okay, so let me take this control signal of first flip-flop as clock 1, second control signal as clock 2. Both are shorted and they are connected to a common signal called clock, right? So in this manner the circuit is built. Okay, so for this reason, where all the control signals of all flip-flops are connected to a common signal called clock, for this reason this flip-flop this counter is called a synchronous binary counter, right? So if when I have taken only two flip-flops, the first flip-flop is used for LSB and the next flip-flop is used for MSB. So if I use one more flip-flop, so that flip-flop output will become an LSB, right? So let me explain this with only two flip-flops, right? So where Q2 is MSB and Q1 is LSB, right? So when I use two flip-flops, in the last class we discussed the number of combinations or the number of output states depend on the number of flip-flops. If I have two flip-flops, we can write four different states: 0 0, 0 1, 1 0 and 1 1, right? So when Q2 here you can observe the Q1 is continuously toggling, right? So that means the first flip-flop continuously toggles. For that I need to connect T1 is equal to 1. For all these flip-flops the inputs are connected to 1, right? Because they need to toggle whenever they get the positive edge of this clock, right? So sorry, I made a mistake. It is not equal to 1, right? So later I'll tell you why it is. Okay, so here Q2 you can observe Q2 is staying 0 for 2 clock pulses and it is staying 1 for next 2 clock pulses. That means it is not continuously toggling similar to Q1. If Q2 also toggles simultaneously with Q1, what happens? Let us say the initial state of both the flip-flops are 0 0. When Q1 toggles, Q2 also toggles. If this condition happens, then what happens? Instead of getting four different states, we can get only two states: 0 0, 1 1. After 1 1 again we will get 0 0, again we will get 1 1, right? So this is wrong, right? So to get all the four states, we need to connect the input of this flip-flop to output of something else, right? Some what we call some additional circuitry is required to not to make this second flip-flop to toggle, right? So what is that secondary or additional circuitry, that we will see now, right? So now see, first flip-flop I'll directly connect and I'll connect it to one signal. Here I'll call it as a count enable, right? So if you want to enable the count, so you have to make this count enable is equal to 1, right? So if I make count enable is equal to 1, the first flip-flop continuously toggles whenever it receives the rising edge of this clock, right? Whenever it receives rising edge of this clock, the first flip-flop toggles, right? So now when the first flip-flop toggles, you can observe in this truth table, okay? So when Q1 toggles, Q2 should not toggle. That means I directly cannot connect this Q count enable to T2. I cannot connect directly to T2, right? So what I'll do here, when T2 remains, or when second flip-flop remains in its previous state, when T2 is equal to 0, right? So how can I make T2 is equal to 0? What I'll do here, I'll take this count enable, and I'll take Q1. Here Q1 is nothing but the previous value. Because to update from 0 to 1, it will take some amount of time, right? So when this flip-flop receives, and second flip-flop receives the rising edge of this clock, the updated value of Q1 will not be taken, right? So the previous value of Q1 will be taken, because to update Q1 or to change Q1 from 0 to 1, it takes little propagation time, or little propagation delay. It might be in terms of millisecond, microsecond, or nanosecond. But suddenly, whenever Q1 receives, or when T1 will become 1, when T1 becomes 1, Q1 will not suddenly toggle, will not change its state from 0 to 1 suddenly, right? It will take some amount of time, because this flip-flop is made up of number of gates, right? So little propagation delay it takes. It might be in terms of a microsecond or millisecond, or it might be in terms of nanosecond, right? So here the time at which the first flip-flop receives the rising edge of this clock, second flip-flop also receives the rising edge of this clock, right? So but here the updated value of Q1 will not be connected to Q2, right? Some additional circuitry is required. So that additional circuitry is nothing but the AND gate, right? So what happens here, if I connect this AND gate, and output of AND gate is connected to T2. Now what happens, let us say initially Q2 and Q1 both are 0 0, right? So this is Q2. This is initial state of the counter, right? So now only Q1, when the first rising edge occurs, only Q1 has to change. That means it will receive the clock pulse, rising edge of the clock. Even the second flip-flop also receives the rising edge of the clock, but Q2 should not toggle as per the truth table of the counter, right? So Q2 should remain in its previous state. What is the previous state of Q2? It is 0, and it should remain in its previous state, that is 0th state, when its input is equal to 0. If its input becomes 1, then second flip-flop also toggles, but this should not happen. I should make a T2 is equal to 0, right? How can I make T2 is equal to 0? By using this AND gate, right? So in the previous circuit you can see count enable is directly connected to all the inputs of all the flip-flops, but here we are connecting count enable to AND gate, and the output of AND gate is connected to T2. So what happens here, even count enable is equal to 1, the output of AND gate depends on Q1. What is the previous state of Q1? It was 0. So one input of AND gate is 0, that means output will be equal to 0 and T2 will be equal to 0. So when T2 is equal to 0, second flip-flop stays in its previous state, right? So now when what will be the next state? Next state will be equal to 1 0. That means when Q1 is 1, the previous state of Q1 is taken. Q1 is 1, right? And count enable is equal to 1. 1 and 1 is 1. So this is connected to T2. So since T2 is high, Q2 toggles. Anyhow, Q1 continuously toggles. For each rising edge of the clock, Q1 continuously toggles, but Q2 has to toggle after 2 clock pulses, right? So now in this case, whenever Q1 becomes 0, whenever Q1 is or whenever the previous state of the Q1 is 0, then output of AND gate will be equal to 0 and T2 will be equal to 0, and second flip-flop remains in its previous state. So after 1 0, I should get the next state as 1 1, right? So what is the previous value of Q1 it is 0, right? So 0 is connected to one of the input of AND gate. Output of AND gate will become 0, T2 will become 0, and Q2 remains in its previous state, right? So this is the simple circuitry for synchronous binary counter for only 4 states, 4 or modulus 4 you can say, which can count only 4 clock pulses, right? So in next slide we will extend this to 3-bit mod 8, and we will make it mod 16 to count 8 clock pulses and 16 clock pulses. Okay, a modified circuit we will see in next slide. So next we will see the mod 8 counter, right? So I will include one more flip-flop here, right? So now the first 4 rows we have already seen, right? Because Q3 is 0. Now I have to verify this Q3, right? So for Q3 to remain equal to 0 or in its previous state, I have to make T3 is equal to 0. So how can I make T3 is equal to 0? We are going to use count enable, and output of both the flip-flops we will connect it to the input of AND gate. So what happens here? Since see, when Q2 and Q1 both are high, when both are high, Q1 and Q2 both are high, and count enable is also high, in that case all 3 inputs of this AND gate will become 1, and the output of AND gate will become 1, which is connected to T3. So T3 will toggle, or Q3 will toggle, right? So Q3 remains in its previous state until the first 4 clock pulses, right? So Q3 will toggle only when T3 becomes equal to 1, right? So and Q1 continuously toggles, right? See in this the column, Q1 continuously toggles, and Q2 also toggles when output of this first AND gate becomes 1, right? So this is the mod 8 synchronous binary counter. Similarly, if I include one more flip-flop, it will become mod 16 synchronous binary counter, right? Short the clock, and what I will do now, I have to use one more AND gate, but in this case I have to apply 4 inputs. One is count enable, second one is Q3, third one is Q2, and fourth one is Q1, right? So and T4 will become 1 after 8 clock pulses. After 7, what we will get? We will get 8, right? So 1 triple 0 we get, right? And Q4 will toggle only after 8 clock pulses, right? So for all these first 8 combinations, Q4 is equal to 0, right? And after 8 clock pulses, the output of a third AND gate will become 1, and T4 will become 1, and Q4 toggles, right? But what is the disadvantage of this circuit here? So as I go on increasing the number of flip-flops, we require the number of even the number of inputs for these AND gates will also increase. So practically we can find 4 input AND gate, it is available. But if I go with mod 10, mod 32, mod 100, right? If I want to design such counters, then we require more number of flip-flops, and we require AND gates with many number of inputs, right? But practically we have only 4 input AND gate. So if I want to build 5 input AND gate, I have to make use of one 4 input AND gate plus one 2 input AND gate, right? So it is not practically feasible, you can say, right? So that is the disadvantage of this circuit. So we will modify this same circuit, right? And we will overcome with that disadvantage, right? So in the next circuit, modified circuit, I will discuss the same operation, but the circuit will be different. Okay, so how can I do that? That we will see in next slide. So here again we'll draw the same circuit, but the AND gate inputs are going to change. Okay, so this is T1, this is Q1, this is T2, this is Q2. Okay, so now here this is clock, and both the clocks are shorted, and they are connected to a common signal called clock, and T1 is connected to count enable. So when count enable is equal to 1, it starts counting, right? So here what we can do, Q1 is connected to AND gate, and count enable is also connected to AND gate, right? And this output goes to T2, right? So what happens here? The same thing. When Q2 is MSB, Q1 is LSB. Okay, wait. So here Q2 is MSB, Q1 is MSB, both are 0, right? Then 0 1, because Q1 continuously toggles whenever it receives the rising edge of the clock. And why Q2 doesn't toggle? Because Q1 is 0 previously, Q1 was 0 and count enable is 1, output of AND gate will become 0, T2 is 0, so Q2 remains in its previous state, right? So now Q1, previous value of Q1 is 1. Now when I am writing this state, the value of Q1 will be equal to 1. We need to consider the previous value of Q1. So this is 1, this is 1, the output of AND gate will become 1, T2 will become 1, and Q2 will become 1, or Q2 toggles, and Q1 continuously toggles, because T1 is continuously high for first flip flop, and it receives the rising edge of the clock, right? So when Q1 becomes 0, again output of AND gate will become 0, T2 will become 0, so Q2 remains in its previous state and Q1 toggles, right? So now if I include one more flip flop here, right? So I need to draw a modified circuit. I need to overcome that problem, right? That is the number of inputs for AND gates were increasing, no, in the previous diagram, right? So that I need to overcome. So what I can do here, I can connect, again I will use AND gate, but in this case the number of input for AND gate will not increase, they are going to remain constant. How can I make Q3 is equal to 1 now? Just think after this state. Let me write the last state of the flip flop, that is 0 1 1, right? This state only I wrote here with one more additional output, right? So 0 1 1. Now I have to toggle, Q1 will toggle because count enable is equal to 1, Q1 will toggle, right? Q2 also has to toggle, that means Q1, previous state of Q1 was 1 and count enable is 1, right? So 1 and 1 is equal to 1, T2 is 1, Q2 also toggles, that is correct. Q3 has to toggle, that means this is 1, right? So this I can connect to directly AND gate, and Q2 I can connect to AND gate. So what was the previous value of Q2? Q2 was 1, so 1, and this is 1, 1 and 1 is T3 is equal to 1, so Q3 toggles, right? So can you observe here, the number of inputs are going to remain same for both the AND gates, right? So even if I draw one more AND gate, one more flip flop, right? So what I'll do here, I'll connect this output of second AND gate is connected to one of the input of third AND gate, right? And second input will become Q3, and this will be equal to T4, and this will be equal to Q4, right? So the problem what we discussed in the last circuit was is overcome, because the number of inputs are going to remain same for all the AND gates, they are not increasing. So this is the modified synchronous binary counter circuit. Okay, so we will wind up this class here. In next class we will discuss some more counters using shift registers. Okay, thank you.